Hi, this is a video on graphs. Now graphs are great. Just like a picture can tell you 1,000 words, graphs can do very much the same thing. They can communicate a lot of information in a relatively small space and in a very efficient amount of time. But there's one thing that it took me years to realize, and that's exactly how useful graphs can be in terms of solving problems as well. So they're not just good at communicating scientific information or data or results, but they can actually be used to solve problems and to understand physical situations and scenarios. I'm going to talk about just a couple specific kind of graphs here today. One of the kinds that I'm going to talk about is a distance versus time graph, or a displacement versus time graph. Now, as I said, graphs can be used to solve problems. Many times when you get a problem, you're going to be tempted to jump right to mathematics, to the kinematics equations, for example. But often you can take those same sorts of scenarios and graph them as well. We'll do that probably not so much in this video as we'll do in class. But you can solve those same problems by knowing how to graph them. So this is a displacement versus time graph. You might see it as a position versus time graph, or I could do x versus time. I could do position. Sometimes I'll do distance. And when I say distance, it usually means displacement. Any of those terms work. The whole idea is your position is changing with time. There's some things that you need to know. You're going to almost always put time here on the x-axis, displacement there on the y-axis. And let's say I draw a picture here. If you look at this, you can see that the displacement is increasing with time. That means that the object is moving, presumably in the positive direction if the displacement is positive. If this line is straight, that means it's moving at a constant speed. Constant speed in this case means that acceleration is 0 and velocity is a constant number. If it is not moving at a constant speed, you'll actually see a curved line of some sort, and there are different curves depending on how the acceleration is going. There's a few things you can figure out from this displacement time graph. Let's say I put some numbers on here just to make it easy. 1, 2 seconds, 3 seconds, 4, 5. There's some things I didn't do that I probably should do, like units, seconds. We'll say this is in meters. 1, 2, 3, 4, 5, 6. You can, for example, just pick a time. Time 3, we're going to go up, boom, and we read over here, and we find that the displacement is probably around 2.7 meters. So it's gone about 2.7 meters in these 3 seconds. 2.7 meters in 3 seconds, you can figure out the speed to that. And there's an easy way to figure out the speed from a displacement versus time graph, and that is the slope of the line. So the slope of a line is considered the change in y value over the change in x value. And this only works if you're dealing with some sort of flat line. If it's a curve, you can still get the slope to the curve, but you're going to get it in an instant. If it's for an extended period of time, you can just look at the change in y divided by the change in x. If you look at the change in y, that's displacement. Change in x is time. Displacement divided by time, just like distance divided by time, is actually your speed, your velocity. So the slope of this graph is going to be your velocity. You can have a positive velocity, just like here. You can have a negative velocity or even a 0 velocity. You had a graph like this. You could even go down this direction. Here are we moving in the positive direction at a constant speed. So v is greater and it's constant. Here, it's stopped. velocity is 0. It's at a stop, so not moving at all, at about 2.5 meters from your starting point. Here, it's moving with a negative velocity. V is less than 0. And that is also a constant speed. You'll notice at this point here, you have returned to your starting point. So you're moving away from your starting point. You're 2 meters up. You stop for a period of time, probably about 3 seconds. And then after that 3 seconds, you walk back to your starting point. You don't stop at the starting point, however. This is not a stop. You just keep on walking. So this graph right here might look something like this. I would walk a little bit at a constant speed. I would stop for a couple seconds. Then I would walk backwards, and I would just keep going until, at this point, I'm gone from the scene. This is a displacement time graph. There are other graphs you're going to see as well. Actually, before I do that, there's some other things that you can get from this too. Let's say you wanted to look at the average velocity, for example. Well, it all depends. If you go up to this point, you've gone about 2 meters, and it's taken you about 5 seconds to get there. Now, granted, you walked for a period of time, and then you stopped for a period of time. But to get the average over a specific time, it's going to be the total distance divided by the total time. So velocity between 0 and 2 seconds, your average velocity is going to be about 2 meters divided by 2 seconds, about 1 meter per second. But your average velocity between 0 and 5 seconds is going to be, you've still gone 2 meters, but it's taking you 5 seconds to do so. So that's going to be 0.4 meters per second. So a much lower average velocity, even though you've gone the same distance. If you want to measure your total displacement, for example, by the time you get back here at your starting point, your total displacement is going to equal 0, right? Because you started at the starting point and you've returned to that starting point. But in doing so, your total distance, remember distance is a scalar, not a vector. Distance at that point is not going to be 0. You've gone 2 meters up, you've stood still for a while, then you've come 2 meters back. The total distance is 2 meters plus, you didn't travel any distance here, 0 meters, plus another 2 meters back. So your total distance is 4 meters that you've traveled. So again, you can find these graphs very useful in solving problems. I want to put up now a different kind of graph. That's a velocity time graph. And a velocity time graph might look very similar to a displacement time graph, but that does not mean that the same things are happening. Velocity, we'll say, is in meters per second. Time is in seconds. And let me give us some units. 2, 4, 6, 8. 2, 4, 6, 8. So one of the first things you want to do when you see a graph is look at the axes. Because a graph that looks like this, for a velocity time graph, is not going to give you a distance time graph that looks like that. Not the same, right? In this velocity time graph, you start at rest. So right here, you're at rest. And here, you are speeding up. And you're speeding up, that means you have an acceleration. You are accelerating. A couple things we know about a velocity time graph. The slope of this line is your acceleration. And if you look at it in terms of delta y divided by delta x, it's the exact same thing. The slope is rise over run, so change in y divided by change in x. Change in y is velocity, or change in velocity in this case. Change in x is time. Velocity divided by time, delta v divided by t, is acceleration. So your acceleration is your change in velocity divided by the time. I'm going to make that delta a little bigger. And that is almost identical to one of the kinematics equations we saw, just rearranged a little bit. Acceleration is change in velocity divided by time. So most of the time you see a graph, the slope is going to mean something. You should understand that. And you can have negative slopes, which would mean a negative acceleration or an acceleration in the negative direction. You can have objects moving at rest as well. So there's lots of different scenarios that you could have for these same kinds of graphs. There's one other thing that you can figure out from these graphs. And I'm going to draw another example in a minute. I told you the slope equals the acceleration. Let's say you pick an area between 0 and 5 seconds. If you look at the area under the curve here, that area under the curve, is equal to the distance you traveled in that time. So for this particular example, you can figure out things like the slope in the area under the curve. So the slope is equal to the acceleration. Let's just pick a period of time, about 6 seconds. You've got, in about 5 seconds, you've gone from 0 to 6 meters per second. So the change in y would be 6 meters per second, and the time is 5 seconds. So your slope or your acceleration, in this case, 6 divided by 5, I'm going to put this in the calculator, is 1.2 meters per second squared. So that's your acceleration for this. And it's a constant acceleration because the slope is a straight line. The area under the curve, this is a triangle. You should know how to figure out the area for a triangle. It's just 1/2 base times the height. So in this case, 1/2. The base is 5 seconds. The height is going to be 6 seconds. 1/2 times 6 times 5 is 15. I made a small mistake here. I don't know if you caught that. 1/2 times 6 times 5 would be 15. But if I look at the unit, seconds times seconds, that would be seconds squared. A distance can't be seconds squared. So I clearly made a mistake someplace. It turns out that this 6, the height is actually meters per second. Sorry about that. So 15, the seconds cancel each other out, leaving 15 meters. So the distance, or your displacement, in this is 15 meters. So you've traveled a total of 15 meters in these first 5 seconds with this graph. Now you can have different kinds of graphs too. So let's say, change the appearance of this graph to look a little like this. The same things hold true as before. The slope is still the acceleration. So here, the acceleration is going to be negative. Here, the acceleration is going to be 0 because it's a flat line, right? Staying at the same speed. Here it's decreasing in speed. Here it's speeding up. Acceleration is greater than 0. And actually, let's see, I'll say slowing down. at this point in the graph, interestingly enough, its acceleration, the slope has not changed, so the acceleration is still less than 0, but it actually is speeding up again because your velocity is also less than 0 at this point. You can just read over the velocity at any point. So at 3 seconds, its velocity is about 4 meters per second. At 1 second, its velocity is about 1 meter per second. At 6 seconds, its velocity is about 2.5 meters a second. So you can read velocity off of all these. In all cases, the velocity is positive until you get here. The only time it becomes negative again is right at that spot. Your velocity is 0. So at this instant in time, this object is stopped. It's also stopped right here. It's at rest. So at rest, it's speeding up, moving at a constant speed, slowing down, but all in the same direction because the velocity is always positive. So it would be something like this. I'm speeding up, I'm moving at a constant speed, I'm slowing down. And then, at that point, you're actually moving backwards and speeding up. Because the acceleration and the velocity are both in the negative direction, so that acceleration is making the velocity more and more negative with each passing second. Now, trying to equate distance and time graphs to velocity time graphs is a little tricky, but you can look at a distance time graph and figure out exactly what's going on. You're going to do some of this in one of the labs as well. Distance versus time graph though. Let's look at this and think about what's going on. For the first 2 seconds, it's speeding up, right? Well, when an object's speeding up, what you find is that the distance is increasing, but it's increasing exponentially. So it looks a little bit like that. Right? So you get a sort of exponential curve. I'm going to flatten that up just a little bit. So that is curved upwards. Curve right there. At this point, from 2 to 5 seconds, it's moving at a constant speed. If it's moving at a constant speed, that should be a straight line. Because accelerated is 0, constant speed. So this distance graph goes with that velocity graph. And at this point, it's slowing down, but it's still moving in the positive direction. So it's slowing down, which means the distance is going to gradually decrease until you get to about 8 seconds. And at 8 seconds, it actually stops. So if it stops, that means that's completely flat because the slope of this line is flat. And then it's speeding up, but in the negative direction. So if it's speeding up in the negative direction, it's going to be curved downward, something like that. So it starts out with just a small change and gets bigger and bigger and bigger. And you notice as it speeds up, the slope gets bigger here too, because the slope of this curved line represents the velocity, because it's distance versus time. Now these are the two kinds of graphs you're going to see most. You also will see acceleration versus time graphs at least a little bit. And an acceleration versus time graph is pretty much the same. The difference being you're measuring acceleration. So acceleration is in meters per second squared. Time is in seconds, good. An acceleration versus time graph like this would mean that the acceleration is changing. But the reality is we're not going to deal with many situations in this class where we have a changing acceleration. In real life, you actually have, it's very hard to have a constant acceleration, so you often have changing accelerations. As you'll see in your lab too. But most of the time when we deal with this class, we're going to have something that looks like this. And that might be a constant line. So here, acceleration is 5 is constant. That would mean you're accelerating at 5 meters per second squared. The other one, see that? If you're in free fall is going to typically have an acceleration of 9.8 meters per second squared. So it's going to be up here. And it's probably even possible to join these together with a very quick change in acceleration. So let's say something is falling, accelerating downwards, but I'm resisting it at least a little bit. Its acceleration might be 5 meters per second, but then as soon as it falls, its acceleration is 9.8 meters per second squared. Or sometimes you might even have an acceleration that's 0. So if we come down here, acceleration is 0. And if acceleration is 0, that means velocity is constant. And constant velocity is nice and makes problems a lot easier. But most of the times when we do problems, we're going to have a constant acceleration of some sort. Whether it's 9.8, 5, 0, it could be negative 9.8 meters per second squared. There are lots of different choices. So those are just a few of the kinds of graphs that you're going to see in class. You're going to also experience more graphing during the lecture portions as well. And I'll encourage you to think about what the slope of lines mean when you're doing graphs. Because it's not always clear what they mean, but they often mean something when you have a graph and you can measure the slope in your lab section. I do want to mention also, when you find the area under the curve, just like you did before, especially for the distance, well, just anything though. I mean, if you were to find the area under the curve of this, for example, we can do it pretty easily because we know that it's a square and it's got 5 on one side, 5 on the other. 5 times 5 is 25. Well, the whole idea, the concept of finding the area of a shape like this is really the basis for calculus. I mean, that's what you do in calculus. When you integrate an equation, you find the area under the curve. And if your equation was just a straight line like this, the area would end up being just the shape of a box, would end up being 25. So if you're curious to know where this comes from, there's a lot of calculus that relates acceleration to velocity to time to position, because you can integrate this acceleration versus time graph and you end up getting a velocity from it just by integrating that area underneath it. That is the end of the graphing video. Thank you very much.